Jennifer asked a question, and she asked, what's the mathematical implication of p proportional to 1? She says it equal to 1. So I think question 1 and question 2 was attributed to Warren. We'll get to that. But yes, but there's, you need to say more. So 1, what's, I don't know if I understand the question, but I can say a lot about it either way. So what's pi mu equal to 1, what's the mathematical implication of this? Okay, so for 1, let's just be a little bit more specific. I mean this proportional to, and I want to remind everybody that mu lives between minus infinity, get rid of that equal, and infinity. So over the whole real number line. So it's not equal. But of course, when I compute with it, I set it equal to equal. What I really want to do is just make it flat and constant. Flat. So that's the whole thing. So it's like, how is the prior placing mass on the real number line? It's saying, at least on the scale of mu, it's uniform. So of course, that's not a uniform distribution. We're not going to do inference off of this. You can't simulate from this on your computer. So it's an idea. It's just placing flat mass. Implication, I don't know what this means. So it's like, what did I imply? Well, I guess I implied in a prior sense that I'm placing equal mass everywhere on the number line. Warren had a really good question that segues into this. And I'll say a few more things about this in a moment. I'll repeat myself a little bit. But this is kind of like almost Warren's question, or at least the part I want to address. So Warren asked, just remember we have lambda is equal to the log of p over 1 minus p. Warren remembers me torturing him with this in inference class, computationally. Took out the log. If I put the log in there, it would torture you even harder. So it's kind of interesting. It's like what scale you operate on matters, computationally too. So if I just asked you to estimate p, it's an easy problem. So, but of course, computing this when p is small or big, it's a numerically unstable problem. If n was small, you might have, p being 1, which you'd see an immediate consequence from. So if you ended up having p was large, n was small, possibly when you plugged in p hat or something like that, it would blow up in your face. So what scale you operate on really does matter. It can matter computationally, numerically, but also it can impact your inferences. And so this is just the log odds. So people use it, some people like it. It shows up as the canonical link function in a logistic regression. So you might be thinking about that. There's some people might call that natural. I have mixed feelings about it. It's like, you don't need to explain things on this scale. But there are some things that we can derive using this scale. And so the inverse of this, if I solve for p, e to the lambda 1 to add I can still do that in my head. Log exponentiate each side. You might ask, like, does the logarithmic scale matter to me? It never matters to me. It just changes everything by constant. So it doesn't really matter. They all have the same asymptotic behavior. Okay. Interpretation-wise, yeah, maybe that might matter. You know, so I always work with the natural log. If you're a computer scientist, you like log 2. If you're a civil engineer, you like log 10. So, all the same stuff. So this is the, does anybody know what the name of this is? A logit function. You see this in logistic regressions. So usually what they'll do is they'll estimate their p's like this. Right here, probabilities of things, and this will have something to do with the regression parameters that lives in there. So x betas. Maybe we'll study a problem like that later on. If you don't know what logistic regression is, you probably haven't seen this, but it's that 0-1 regression. A lot of people transform the problem into this. Shows up in generalized linear models. So this is the natural link for a 0-1 regression. And if it was an older department, we would think that that was really important. You know, there's a lot of ways to do 0-1 regressions, and I don't know if logistic regression is all that anymore, especially with like neural nets floating around, you know, that pull out the linearity assumptions. Okay, enough about that. Logit function. Question is what is, if we ended up having pi p, that's really abusive with the notation in the thing. So I kind of like to just fudge around with the notation to see how many different ways you can see the same thing. So it's kind of one of those things you just have to get used to. So pi p, I'm saying let's make this equal to 1 right here. This one is equal because it's on a compact set. It lives between 0 and 1. And so we can normalize that. So this is just a uniform where p lives between 0 and 1. So uniform distribution. And I think at the beginning, when we started having this conversation, people like this. Feels good. I've said I like the other one better. It's pretty uniform in the middle. You know, but over by the boundaries where everything gets complicated and asymptotically misbehaves, you might want to penalize, you know. And so, but this is the beta 1-1 prior. So if Warren asked this question, is the answer to part 1 the implied prior for lambda? And it is, and we can work through that calculation in a second, if you like this. So if you like this and you're advocating this, and somebody asked you to operate on this scale, then what you're figuring out is the implied prior. So yeah. But what would you argue? Would you argue this thing you wrote down, or would you argue that? You know? So there's usually a scale that people understand a little bit more. So if you liked uniform on P, then your implied prior would be this thing. And this is just a transformation of variable. So Bayesians are always working on probability scales. And so we know probability pretty well. We know how to write down likelihood functions pretty well. So let's just work through it real quick. So part 1. And then I'll try to connect it back to what Jennifer asked. So part 1, what's pi lambda? So I didn't say anything about priors, but yeah, this is the way you're thinking about it. Maybe I did say that this was a prior. So it's just a distribution. And this happens with any distribution, but yeah, maybe you apply that as your prior. You know, what's this thing right here? How do you do it? I like to, at this point, name what my pi's are, so I know what this function is. These are different, you know. So usually when I have 2 pi's floating around, I'll nickname them different things. This is function for p, and this is function for lambda. They're not the same functions. So one is a transformation of the other. So we want pi lambda, lambda. And how do I find that? I find it like this. I take pi p, whatever that functional form is, and I take my lambda, but I rewrite it in terms of p. So lambda is this. Usually there was a lambda inside of this, right here. And I'm going to rewrite it in terms of p. So I got rid of my thing. So p is equal to e lambda over 1 plus e lambda. It's probably important to try to think about where lambda lives, just real quickly. So where does this live?
Negative infinity to infinity.
Yeah, exactly. So it lives on the whole continuum. So we're mapping the unit interval into this site, this logistic curve. They look like little s's. So I'll rewrite this just a little bit differently if you want to re-see it. So I could divide everything, the top and the bottom, by e lambda, and sometimes you're used to looking at it like this. 1 plus e to the minus lambda. They're equal to each other. So you can kind of see is this thing gets big, and when it gets small, you can kind of see how this impacts p. So if you just want to wiggle one knob, you can isolate that lambda. Okay, so this is going to be whatever p was in here, this function, but I'm not just going to take that p and shove it in there. I'm going to rewrite it in terms of this function right here, e lambda. This is going to be a function of lambda, so there cannot be any p's over here. So e lambda over 1 plus e lambda. And then I have to multiply by, what I'm always saying is the Jacobian. It's the derivative in 1b, and you need to make it positive. So does anybody know why we get this? Like, why does this happen? So it's like, it would be really nice if I could just take my functional form, solve for p, plug that thing in, and that's the density function. But instead, you need this derivative right here. And this is going to be the derivative of e lambda, 1 plus e lambda, d lambda. So why does this appear? Just since we're in a review session, we can take a little bit more time to think about more basic stuff. We're jumping between your answer and Warren's answer, so plenty of time. So make yourself comfortable.
I guess that a small hole because my mind seats for the snake.
Oh, yeah. Mine did almost too. I had to double check. Okay, what we're talking about is, you would ask this question, what's the mathematical implication of this? What I said was, it says that on mu scale, it's uniformly distributed across the whole thing. And that's about all I've said. Warren asked a question concerning number 2, and I think he was more calculation oriented than I'm answering, but there's a lot to talk about right here. Is, yeah, this would be the implied prior so long as you liked uniformity. So you're almost caught up, and the video will be there. So this is how you do a transformation of variables. So in what we're saying is we take p, we solve for it, i.e. we find the inverse function. We're trained in that. There it is. But we always need this factor. If this is a density. If it's a PMF, a mass function, you just do the inversion and you shove it in. You do not rescale the space. So for discrete distributions, we do what you want, but if it's a continuous distribution, if it's a random variable, we're really interested in the area under the curves. We need this thing. One answer is it's the chain rule. So it's just the chain rule in disguise. If you follow the fundamental theorem of calculus, it is the chain rule. It's what you're actually doing. If you want a lecture on that, just ask me. I can give you that. Here's a more intuitive way of thinking about it. When I transform the space, each little cube, hypercube, in this case is just area. But I morph the space and I rescale it. How am I rescaling it? How am I stretching the space? The derivative is the answer. So that's the stretch factor. So if you end up thinking about, just think about like a straight line, you know, ax plus b. something like that. X is your random variable. How did you just stretch the space? The b didn't do anything. It just shifts it. But you rescaled it by a, what would the derivative be? It would be that derivative with respect to x. I'd have to solve for everything. It would be inverted, so it'd just be that 1 over a term. That's how I'd be stretching it. So I think that's pretty easy to think about. In high dimensions, this is a Jacobian, so you end up just tiling all the partial derivatives, and then you take the determinant of that. Absolute value. Why absolute value? The chain rule, it always comes out positive if you do it right. This little heuristic rule, you can introduce a negative sign. But if you follow the chain rule by hand, it would always be positive. So you can try to convince yourself of that. The determinant thing, that's just areas again. So from calculus class, probably when determinants were first introduced to you, is they told you things about these three-dimensional rhombus-looking things. And they'd have you compute the area and do stuff to it. And how did you compute the area? You took a determinant of its vector space. That's the same thing that's happening here in height. So it's just the areas that are getting restretched. So this is a scale factor. So you have to rescale the space. If you want the more technical thing, why is it the chain rule? You can ask me about that in a future reading. We're going to be transforming random variables all the time. So it's good to understand this more than just a formula. It's also more than one way to do it. Sometimes it's easier to do other things. Possibly I could take the derivatives with respect to p. Maybe it's easier here. I could take this. I could take the Jacobian with respect to p, invert it after I take the absolute value, and then solve for lambda and plug it in. So sometimes derivatives in one direction are easier than derivatives in the other direction. So, yes, please.
So for a scalar, you don't have to take a determinant, right? It's just the absolute value.
It's just the absolute value.
Okay.
Yeah, it is the determinant. The determinant of a 1 by 1 is just that thing.
Okay.
So yeah. So I like to just think about it in high dimensional space. So I usually, every problem when I talk about it, generally I like to talk about continuums, and generally I like to talk about at least 2-dimensional space, just so that you can see the patterns. And I'll just say it that way. I'm never going to ask you to do anything too crazy on a midterm, but it's still good to understand what we learned in calculus in the context of probability. So just remember when you did transformation of variables in calculus class, this term did jump out. This would be like your dx term that you have to reintroduce and apply the chain. So it is the exact same rule. So when you integrate over these spaces, you have to make sure the area is preserved. Okay, so this is really easy, because this function right here was just 1. And so that's still 1. And then I just need to take this derivative, and I'll let you work through it. So I have no idea how to do the quotient rule, but I know the product rule. And so you'll work it out, and you'll recognize something. So the answer at the end of the day is going to be this. Back to Warren's question. So he said, is this, which is the answer to that, which is the answer to the question, is that the implied prior on lambda? Yes, if you're arguing for this in the first place. So the key take home is you think you're placing uniform mass on a parameter. It feels good to do that. Yeah, just make it 1. Then I'm just always doing inference off of the likelihood. Can't always do that. But if I transform the problem, you have a different answer. So you need to be more thoughtful. So why do we like thinking about P? I don't know. Maybe it's kind of natural. But some people like to think about this. And so then I ask you to do the problem in the other direction. Imagine somebody told you to place a uniform prior on the log odds. What would your implied prior on P be? And lo and behold, it's some beta. You can recognize it as a beta. If you write it down and don't recognize it as a beta, that's okay. We're not going to freak out. We'll just, if the answer is right, it's right. But you can probably recognize what distribution it is. Has anybody done that yet? What is it? Beta what?
Half-half.
I don't think so. So I don't think it is.
Yeah, but what I got was that it was, the probability mass was very large near the 1 and 0, right?
Yeah. So
Okay.
so you can draw it out. But again, the answer for the other way around. So part B, if somebody said, well, why not do this? Now this has to be an improper prior because you're talking about negative infinity to infinity. You cannot place a uniform on that space that normalizes. So if you did that, and I wanted to know what's this, pi p, this would be uniform times the derivative of log p over 1 minus p. I'll let you work through that derivative. But this will be some beta. Just to be sure. Absolute value. So your answer will be this thing. So check it out. So not a hard problem. Key point is if you place uniform mass on something, you better have a better reason than it just feels good. Because unbeknownst to you, you placed mass in some other transform space. So you've placed mass in a way that you maybe haven't anticipated. Now this is always true when you work with transformations anywhere. So a lot of people, like in my first regression class, I thought it was really cool. You know, they taught me all about the normal distribution. And it's like, well, what if your stuff doesn't look normal? And they'd have a couple of cookie cutter examples, and then they would introduce the Box-Cox transformation. So power things, do things to things until it looks normal. Okay, super. So that's great. Maybe a machine learning algorithm will like that. But when I go to like understand the confidence or something like that, if I were into that sort of thing, so that's under this transform thing. And so if I want to think about what those bounds do in the original space, you can't just transform because you're morphing mass. So you can't just do that. So anywhere you're at and you're doing transform variables, and you really wanted to think about it on the other space, there's this other layer to everything. So for the Bayesian, it's how do you place the prior? On which transform space do you do it? Now back to Jenny's question. This one we picked as uniform mass over the whole thing. It's equally weighting every point in mu. And that probably looks and feels pretty good. And Fisher thought that was a good idea, and I'm not going to debate him. I think it's a good idea as well. I think that he says no prior. Well, I never multiplied by 1 in the first place. You can't tell I multiplied by 1. This is not a Bayesian posterior, but he ends up giving you a magically upgraded distribution, you know, on the parameter space. And he called this fiducial statistics. It's bogus. You know, it's like, no, you have to, I think you have to do Bayes to get there. Saying that, the inferences he made, I think, were good. So, you know, so this is where Bayesians get into a lot of trouble. Like, what's the semantics of this? What does it mean? And we're going to lecture you on what everything actually means. This just means uniform mass on the scale of mu. It's not uniform on the scale of 1 over mu. Let's just look at that real quick. So if you were interested in this parameter, so just imagine, I don't know who would be interested in the inverse mean, but maybe they would, you know? So if we ended up having pi mu proportional to 1, and then I think about maybe some transformation psi is equal to 1 over mu. Let's do mu squared. I'm going to think about this. I'm just going to consider a truncated model. I don't want the 0 to be a big deal to you guys. So I'm going to say we're only thinking about mu's greater than 0. So this is coming out of a truncated normal model or something like that. So I don't want you to get too caught up in the 0 of all of this. I have to break the space. So It's not the point I want to make. So let's imagine I've got 1 over mu. Somebody's interested in this parameter, 1 over the mean. So I'm going to transform, and I'm going to figure out what my prior looks like right here. So this is going to look like pi, and this one's for mu, just to be specific. I'm going to solve for mu right here. That's 1 over psi. That's the inverse function. I get to do that because I made it all positive, so no problemos. There would be 2 answers if I didn't make it positive. So then I just take the derivative with respect to psi. If you like. And so this thing is 1. So this is the derivative with respect to psi. What's that? Bring down the negative sign. Decrement by 1. So this, after I take the absolute value of everything, would be 1 over psi squared. So the implied prior on psi is 1 over psi squared. And often, once we get to Jeffrey's prior, we'll ask these questions like, does this make sense? You can go to my lecture from last year. No, 2 years ago you have to go to because I couldn't interact. So 2 years ago. Does this answer make sense? Everybody, yay. Does this answer make sense? No. You know, I don't like this answer on psi, but I like that answer. They're the same. They're equivalent to each other. If you're logical and you understand the mathematics, if you like that, you have to like that because they're identical to each other. So if I place uniform mass on mu, it's equivalent to, if I'm thinking about the inverse scale, to placing this quadratic hyperbola mass. So on psi, you know, what does it all mean? It means that it's uniform on mu. So if somebody gave me that, I might be inclined to think about that. I would have an answer to this. I'd be able to rationalize my way through it. And here's what I would think. I would write down the model. And I would think about what the likelihood looked like. So the likelihood might look like this. E to the minus 1/2 x minus mu, but I changed the meaning of it to 1 over psi. So 1 over psi is equal to mu squared over sigma squared. So I'd be staring at this. So my likelihood function for 1 over psi given x and sigma squared, so it'd be proportional to this. I wouldn't need to look at the normalizing constant because it didn't involve mu in the first place. So I just switch it over. So the likelihood, I do just rewrite it. You don't restretch the space because you're not integrating under the curve. So it's when you integrate, you need to account for the stretching of the space. Likelihoods, you are not allowed to integrate over them until you turn that thing into a random measure. So when you see people do it without introducing a random measure, you can just think, oh, they placed a uniform prior on everything they integrated over. I wonder what the impact is. And if they've never thought about it, I bet you could do that. So if I were working with this likelihood and I wanted to infer psi, and I used this prior right here, I would have equivalent answers to everything I gave you when I used the uniform prior on mu. It'd just be transformations of each other. Once I make it a posterior probability, I need to reintroduce the Jacobian. So this is going to look like, sorry, this is for psi, not 1 over psi. So the posterior distribution on psi, with just one data point, would be proportional to e to the minus 1/2 x minus 1 over psi squared, sigma squared times 1 over psi squared. So I could work through this, figure out what I just wrote down. This is the prior, this is the likelihood. And if I transform that thing onto mu scale, the answer would be, I'd get a normal centered at x with variance sigma squared. They'd be identical to each other. And I'd have to transform it. So I would stare at this and I would think about the nature of the parameter. And I'd say, well, psi is not a shift parameter. Psi, 1 over psi is a shift parameter. So I'd start thinking about that. And I would think about what I was going to do with that parameter, how I was going to interpret it. It's a location parameter. And I don't want to influence that a lot with my prior beliefs. So I don't want to inject a lot of information about that. If I had information, then I might use the conjugate form. And then I would have to talk about how much information I wanted to include into the analysis through its variance parameter. So I would instantly think, whatever this thing is, it's a location parameter, 1 over psi. I would change transform it to just mu is equal to 1 over psi. And if somebody told me they liked this belief, I would transform and go, oh, they picked the uniform prior on that. And since it's a location parameter, a uniform distribution, I can slide it left and right, and I can't tell the difference, i.e. it's shift invariant. That's a good idea. So location parameters should have flat priors, unless you know something about that parameter. So that would be the most typical thing people would do. Scale parameters usually have a 1 over that parameter as its prior. That's scale invariant. So I'd say the mathematical implication of pi mu is proportional to 1 is you have a location invariant prior. There's other ways you can think about it. It's also the limiting distribution of the conjugate, where I'm taking sigma squared and blowing it out to infinity. What you're doing is you're losing all information about where you centered it. And so I guess that's good. We're going to learn later on, this is also the Jeffreys prior. This is also the reference prior. So that's kind of good. This is true in 1D. So a lot of these things aren't true as you start moving up dimension. But in 1 dimension, what it means is in the Kullback-Leibler sense, the posterior distribution is moving away from the prior as fast as possible. And so that density function is moving away. Keep in mind the density function is not the parameter itself, it's the whole thing. It has all the information in it. So that posterior is able to steer away from the prior very quickly. That's good. So that's in one sort of measure sense. There's other measures, and it wouldn't be optimal in that measure, but in some sense it's moving very fast from the prior, the posterior. That's good. So there's lots of other good reasons to think about uniformity. I guess it begs the question, is P, is that a location parameter? It is the expectation of the distribution, but it also drives the variance of the distribution. It's just this one parameter model. So it has things to do with the location and the scale. It's telling you about both of these things, how diffused it is. So P has something to do with a lot of stuff. It's not just compartmentalized all by itself. The real issues are in this space is if P is small or P is big, you're going to have funny issues arise. So if you liked your intervals to cover very, very well, you might like the beta half-half parameter. So, and that does pretty good all the way across your whole spectrum. So I would say, in that case, I want that. I don't really want this good feeling that I placed uniform mass over P. I really want the property of my inference to be really good. And so, in that sense, while there's a lot to think about with Bayes, just based off of transforming uniform priors, and no, it's not that simple. I do like likelihood functions. I was already convinced of that, but now I have to think about how to build in the penalties. So I think that kind of makes sense. There's boundaries of your space, they have different impacts. Once you have parameters kind of like commingled with each other, they have something to do with each other in like interesting ways. You need to be thoughtful about how you're regularizing that space or how you're penalizing it. I guess the one probably not great choice was to call this a prior distribution, and to explain it as Bayesians are people that inject prior beliefs into their analyses. I really wish we could take that back. You know, it's like, it doesn't sound good. It's like, let me find ways to bias the analyses. You are biasing the analysis, but you can bring down variance and you can control other things. And so in some sense you're biasing, you're penalizing, but you're guaranteeing other things for it. So it's like, I don't know, I kind of think of it as the prior distribution has some knobs, and I get to turn them, and it's going to impact my posterior inferences in particular ways. And at the end of the day, that's what I care about. So, did I get the right joint set? Did I tell you where the parameter is? What I really like in Bayes is once we have a posterior, once we study prediction, we're going to see we can take all the joint information and all the relationships, and we can average over them in just the right way and make better forecasts. So we can combine all the information and not just like silly ways. You know, it's going to give us a coherent probabilistic framework to work in. So somebody might say, why do you like probability theory? There's nothing better so far. Fuzzy logic, chaos theory, they've taken their stab at it. And it doesn't scale well to high D. You can probably come up with something in one dimension, but they don't work well in high dimensional spaces. And this axiomatic system that Kolmogorov gave us is pretty good for prediction. Cool. Anything else? Jenny?
Professor, for this time you being proportional to 1.
Yes.
Can't people argue that it's some type of, for instance, beta distribution or some type of gamma distribution?
I don't think so.
7,
So a beta lives between 0 and 1.
okay.
And a gamma lives between 0 and infinity. And this thing is living between negative infinity and infinity. So I'll write that down again. Oh, it's here. Convenient. Yeah, so that's not a beta. So there's little things that I check on every distribution. And the first thing I ever check is bounds of support. You know, where does it live? So it's like sums of Poissons distributions, they're Poisson, right? Sums of Bernoullis or other Bernoullis. They average over their probabilities depending on how you're mixing over them. Sums of normals are normals. You know, so you can kind of start playing this game for a while. It's like, huh, what about sums of betas? Are they beta? They're not. Why? Because a beta lives between 0 and 1, and a sum of 2 betas is going to live between 0 and 2. So you've already changed the space of them. So, you know, and it's kind of funny. It's like asymptotically averages, or even just large sums of betas start to look normally distributed. It's kind of cool. So we use that result all the time. So I think you're on the right track. You're learning your distributions. So that's the first thing I ever check is, does it live in the right space? And if it doesn't, then I know it can't be that distribution. So I don't know. This is not equivalent to any proper distribution. The best way I would explain it is it's the limit of the conjugate prior. So where I'm taking the conjugate prior and I'm taking a limit of the variance. As the variance goes to infinity, it's getting flatter and flatter and flatter and removing all information about where you center that normal. As the variance gets really big, you can't tell where the normal was centered. If you don't like infinities, if you're like, nope, it's against my mathematical belief system to use anything with infinities, that's okay with me. Just take the biggest number you can think of, exponentiate it to that number, do that number of times, and do it again, just for the heck of it. And I'm pretty sure whatever number you're trying to infer in reality isn't that large or that small. And so you can take a normal with that variance, that gargantuan number. You know, there's some bigger number than you can think of. And so if whatever you think you're inferring, you know, just make sure the variance is much, you know, way out there. So really, in Bayes land, the likelihood's going to take over as you get more and more data. If you place 0 probability somewhere on something, the likelihood cannot take over that. Likelihood times prior, if the prior places 0 mass, you're still going to have 0 mass. So anywhere you think there's a plausible answer, put mass there in your prior. And probably make it relatively diffused if you're uncertain about things. So if you do this process of just take a normal distribution, center it wherever you want, and make this variance so large, and then if I say do it again, and make it larger, you will converge to the answer that you would get using this. And you'll see that. So we could work out the full, I guess we did. We worked out the posterior mean. So what was the posterior mean for the normal case? So expectation of my posterior given, I'm going to write it down, because this is on your homework. You're going to be working through this. You're finding the posterior distribution of this where you've collected n data points. The easiest way to do it is probably work in the sufficient statistic form, work with X bar, and you'll have your answer in one step. But if you work through it and you work through the product, take the product into the sum of the exponent, drag it through, recognize your quadratic term, recognize your -2 linear term, you'll come up with this. So this is going to be sum of the xi's over n, that's x bar. It's going to be scaled to whatever its precision is. And precision is going to be scaled to that. I'm going to divide by the variance. Plus mu naught that's my hyperparameter over sigma naught squared. So it's being scaled to its precision. This is a weighted average of those two things, so this is going to be divided by these weights, the weights added up. One over sigma naught squared. So what I'm telling you is to take sigma naught and make it big. What does it do? It cancels out the impact of mu naught. So you can't tell mu naught's there if sigma naught's very, very big. This thing is going to get astonishingly small. And you can see the n floating up to the top and making that big. So it has all the weight. This thing is converging to true mu. So this converges to the truth. So Bayesian, if you're working in the conjugate form, if you believe very strongly you should anchor this, maybe you don't have a lot of data, you know something about the answer, you might be able to put it in there. I don't do that. Like, I don't know if there's any answer where I've said, I'm going to include this. But if you did meta-analysis, you said from this other study, they found this, I want to update that with more information. So I have another data source, and I'm going to include it here. So this converges to the true mu. And so asymptotically, even if n was just getting big, even if I had a lot of mu naught was big or something relative to that, n would eventually take over right here. But to Jenny's question, what does this mean? To me, this means that this is going to infinity. So we at least have this framework. Identify the conjugate prior. Turns out the reference priors are going to be limits of conjugate priors. So that's kind of cool. So the conjugate forms are useful. And so for, really what we're doing in statistics is like we see data, and then we have all these like building blocks that we're going to use to try to model that data. They're all different types of probability distributions. So we're going to layer them together in just the right way. we're going to try to infer all that stuff. We're going to think about the nature of those parameters, and we're going to do Bayes on it, and we're going to have all the joint information about it. Any information that I think that I'm encoding into something, I'm going to check through a sensitivity analysis. So if you ended up wiggling around mu naught and it dominated your answer and it wiggled your whole answer around, changed your error rates in your simulation study, I'd say it's probably not a good choice. So how do we make it insensitive? In this case, sigma naught to infinity. Seems to work. What's the interpretation? It's an improper uniform distribution. So not a distribution. I guess that's okay. So, I thought that was really weird when I first saw it. It's like, that's not fair game. That is not Bayes' theorem. I learned that a Bayesian did this other thing. So the whole Bayesian game is to figure out your priors, what their impact is. But there's more to it. So I think this class is, again, a fiction. I'm at the chalkboard. I know what F is. So the reality is we don't know F. We don't know the model. So we're going to see data, we're going to take all these building blocks, we're going to layer them together, and we're going to know the properties of all those building blocks. And know how they affect, you know, the variance of everything or whatever parameter is you're interested in. We build a likelihood function. We usually do it because it's relatively simple. It kind of explains and answers our question. We pick priors based off of properties that we know, that we want to guarantee. Then we compute everything. We see how well it works. And if it doesn't work well compared to the real data, you change your model. You just iterate back and forth. So a real Bayesian is somebody that's looking at a lot of model diagnostics. So they're writing down models, understanding the knobs, how to turn them, trying to understand the impact of everything. You know, so that's what a Bayesian actually does. I like linear shift parameters because I can interpret them. Stuff like that. We kind of go back and forth. So in this class, I'm just going to teach you what the properties of all of these decisions are. Eventually, I'm going to teach you some computation. Good enough? Anything else?
I didn't follow. So where does this equation come from? I want to understand.
This right here, this was the quadratic term from our normal analysis. I'll just write it out. This is problem 1 of your homework. A good problem to know how to do. You'll know how to do it soon enough. It really stacks into problem 2. But if I had xi's coming from a normal distribution, mean mu, variance sigma squared, I get to see n of them. If I ended up picking my prior to be a normal with mu naught and variance sigma naught squared, this would be the answer to this thing right here, the expectation. Mu given all of my x's and sigma squared. So how do we do that? We write down the likelihood, multiply it by the prior. There's this 2-step thing. You'll get really good at this. Use these equations all the time. I'm always juggling normal equations and recognizing where they centered, what's the variance. So in a common filter, you do that like 17 times, you know, in each step. It's really 4. Looks like this. The likelihood times the prior. So this is going to be proportional to e to the minus sum of the xi's minus mu squared over sigma squared. There's that 1/2 floating around in here. I goes from 1 to n. This is the likelihood. This is just the product of all of these things. 2 pi sigma e to the minus xi minus mu squared. There's a 1/2 in there. Sometimes I forget to write it. But that's just the product of this. I simplified it, got rid of the normalizing constant. That's this. And my prior looks like this. e to the minus 1/2 mu minus mu naught squared over sigma naught squared. This is a normal. How do I recognize what's normal? I isolate the quadratic term. The inverse of that is the variance. I multiply that by the minus 2 linear term. Keep this minus 1/2 factorized out of all that. So it always appears, just shove it to the side and keep it there. Look at the minus 2 linear term, multiply it by the variance. That's this thing. I erased part of it, x bar over sigma squared over n minus plus mu sigma naught squared. So when I take the variance term, the 1 over the quadratic term, it's this thing. This is the minus 2. That's the linear term. You'll get quick at that. In the regression problem, you're doing the exact same thing. If you put it into matrix notation and you know what the quadratic term in the matrix notation is, this won't be that hard.
Since you mentioned the regression problem, what exactly is the aim for that question? Some of you don't get it.
I guess I just want you to work it out and go, oh wow, a Bayesian under a flat prior would come up with the exact same regression formula that everybody else uses. So the aim is just to make you connect to things, but I'll just write it down real quick. The likelihood I really just tear through the chalk with this? I'm stashing it here. It's going to look like this. E to the minus 1/2. Depends on how you want to write it. So y minus x beta. I tried to explain that a little bit if you're unfamiliar with it. This is going to be sigma squared times I inverted y minus x beta. That's what a multivariate Gaussian looks like for y. That's easy to write, re-express just like that. I threw out the sigma in there just so that you can see there's another problem coming. If it wasn't multiplied into the identity, you'd get the generalized least squares answer. You'll see that later on in this class. But here's the likelihood in terms of beta. So it's quadratic form in beta. Beta was a scalar, you'd see it getting squared. Oh,
Transpose.
so what do my vectors look like? This one's going this way, this one's going this way. So that's a scalar up there. My prior is flat, so my posterior is this. So beta itself is not just a linear shift, but it is shifting this whole block. And so the x's are given to you in these typical problems. You're supposed to be thinking, the x, I have no measurement. It's always a place for improvement. So you probably have uncertainties in your x's. That's why statisticians are always giving like people these optimistic answers. You know, oh shoot, we're way off on the error rate. Maybe we need to account for that. So that's how science progresses, I guess. So no information on a shift scale on the betas. And the betas, that's probably the scale you're going to interpret it on. Nothing comes from y is equal to x beta. That's not how data comes, but it's a decent description of it. So we kind of like it. And then we can interpret our betas, our contributors of the sum of the xi betas on a linear scale. You know, we can see them all on the same scale. So we like it because of interpretation. It's a very easy place that you can usually go and improve on somebody's analysis. Do something more sophisticated. It's been going on for a long time. For a posterior distribution, it looks like this. It's proportional to this thing But instead of thinking of y as the argument, I'm thinking about beta as the argument. I can see that it's a quadratic in beta. So this is just going to look like e to the minus 1/2 y minus x beta transpose y minus x beta. If you're into optimization and you're studying this problem, keep in mind they're just penalizing the squared residuals. This is a monotonic function of the squared residuals. So these are the residuals right here. They're being squared and added together. And that's what this formula looks like. So I would keep it in matrix notation though. So what does this look like in terms of beta? I'm going to rewrite it in terms of its quadratic terms and its minus 2 linear terms. We can write them all down. E to the minus 1/2. Let's just write them all in there. I'll do the y's first. This is y transpose y. This has nothing to do with betas. That's our constant term that we don't care about. This is going to look like minus beta transpose x transpose x beta. There's one of them. So remember, when you transpose, you have to flip the order of everything. There's another one over here of these. I'll just write it out. There's another thing in here, another quadratic term. So this was my first beta transpose everything. This looks like the transpose of the other one, but this thing is a scalar right here. So this shows up twice. Or this one, no, sorry about that. There's two of these other ones. So y transpose, beta transpose, x, and then I did this wrong. Y transpose was first, x beta. So this one by that. This is actually plus. That's negative, negative. So then I have this other one. Minus beta transpose, x transpose, y. Guess I was jumping the gun. Probably want to hold on to my sigma squared and all of that. This doesn't matter. I can factorize that thing out because I've written this only up to proportionality. These are the same right here. They're both scalars. This is the transpose of the other one. So I'm going to write down the one that I like to hold on to. You'll always need to check out and make sure your dimensions are right at the end of the day when you go and you pre and post multiply. But this is going to be minus 2 of those things. So this is my quadratic term, and this is my minus 2 linear term in matrix notation. So I guess the point is to just work through this in high D, give you an application to regression. I will have you carry out regressions in this class. I'm going to teach you how to do more sophisticated regressions than this, though. So the quadratic term is this thing right here. So the variance of beta, this is a matrix. So there's more than one beta. It's just going to be x transpose x sigma squared inverse right here. So of course, in regression class, they might teach you about cases where x transpose x is not invertible. So that means there's a ridge in the likelihood. So be careful in that case. Pick a regression class, they'll teach you what to do if you have a ridge. I'll teach you what to do later on in this class too. And then the expectation, this is the big look. Make sure you get your dimensions correct in all of this. So this is going to look like x transpose x over sigma squared invert x transpose y. This is the stuff multiplying the -2 linear term. So x transpose y, this is the variance. And there was a sigma squared in here as well. This one gets flipped upside down. So you get this at the end of the day. And to some people, they're astounded, you know? So it's the Bayesian mean in the posterior is the same answer you get from maximizing the likelihood. How could you have told? Well, it's a normal distribution. And so the peak of the normal distribution is the mean. It's the median. It's the mode. And that likelihood surface, the Bayesian interprets just a little bit differently. They say all the area underneath that represents the probability of where you believe the betas live. So you get a probabilistic interpretation on it as well. So not just one answer, but then where you believe the betas live and how they're associated with each other. So they'll live in these ellipses. So that's kind of cool. So one step further, but you carry out this little find the variance, find the expectation. And these are your normal equations. So you might have seen those before. I remember when I learned this for the first time and there was just an intercept and there was a slope. And they had all these equations I had to remember. It was like sum of the xi's with the yi's. And then once I learned linear algebra, I was like, sweet. That is the whole point of linear algebra, is that you can do these sums really quickly. So the calculus is a lot easier to do. What else you got?
I just wanted to make sure I got this really right. So essentially, this question just shows that, I guess this problem, my first time seeing this, I'm a bit surprised, you know.
Yeah.
Because usually when you do linear regression, you come up with that thing, right? That
Yeah.
you say that is your estimated data.
Yeah.
But I guess what this question is getting is, we're not just finding that, but finding a distribution
For the betas. So the betas are centered here at x transpose x inverse x transpose y. And the variance of everything, well, it turns out if you ended up looking at the variance of the MLE, if you looked at the variance of this thing, it turns out it is this. So they're exactly the same. In Gaussian land, the Bayesian and the maximum likelihoodists agree with each other, is what this all kind of says. So the maximum likelihoodists, they're going to be understanding the variance of your estimator. But the Bayesian is interpreting it as the variance of the betas, which is kind of interesting. So it's different, but you can have both. I know what the variance of that estimator, depending on how you came up with it, I can tell you. But the Bayesian takes it one step further and interprets it as a probability surface for those betas. It's probably what you think anyway. So if you think about a normal distribution, and if you use a flat prior, and this only happens in distributions that kind of look like this. So e to the minus x minus mu right here. And I could plug in x bar if you wanted to. Sigma squared over n. It's equivalent to taking that big product. The x's, the non-Bayesian is always just thinking about the random distribution of x bar. It's centered at mu. The Bayesian multiplies by their prior. In this case, probably 1 on mu. And then they interpret, this is the distribution over mu. It's centered at x bar. And that's how the confidence interval people build their confidence intervals. But the reason we agree and we get the same distributions is because we're symmetric in the data space in mu. So it's kind of a coincidence. So in normal world, where everything's Gaussian, everybody agrees with each other, regardless of what your assumptions seem to be. So like, if you're working with method of moments estimators, you're probably going to come up with the same answer. If you're a Bayesian, and you go through this long deliberation about flat prior, you're going to get the same answer. If you're a maximum likelihoodist, you're probably going to do the same thing, and just your interpretations are different. Later on, this framework that Bayesian's working in, they can apply it anywhere and always do the exact same thing. They're never really changing which framework they're working. So I'd say in terms of just ease of explanation, the Bayesian's giving you a probability on the things you don't know, and maybe you like that. So that's why for confidence intervals and for credible intervals, for the normal model, Bayesian gives you the same exact interval, but it has to do with the symmetry in this space. And if it's not symmetric in the sufficient statistic in the parameter that you're inferring, and you're not placing uniform mass on everything, the Bayesian and the non-Bayesian are going to come up with different answers. Question is which one performs better. So I think at the end of the day, that's what we really want to check, is not just all this thought process. Interpreting things is nice, but let's check the performance and see how well it works. And that's kind of what we're doing with the beta binomial problem. I'll give you a beta half-half prior. We're studying coverage. Voila, Bayesian wins the frequentist game. So, my goodness, that can stir up a lot of people. They'll argue over it. I'm not sure why. It's like, it's a good answer. If you want to derive it differently, that's fine. So, but Bayes is a coherent probabilistic framework. They give you the same answers you're familiar with in problems like normal problems. Later on, when we get to hypothesis testing, there's going to be gross disagreement. And when we move to prediction, the Bayesian will have an advantage. So those are places where the Bayesian can really win out. Low sample size stuff, the Bayesian can win because it's a conditional answer, it's not an asymptotic answer. And you might think, well, we live in the world of big data. As dimensionality of problems grow, your sample size is effectively getting smaller. You know, so how much data do you need to overcome a problem that lives in 2 dimensions versus 1 dimension? To have the equivalent, you need n squared data points. In 10 dimensions, n10. You never have that, you know. So if n was reasonably large, you know, n to the 10 would be huge, so you're in this huge vacuum. So a lot of problems are high dimensional, which effectively have kind of smaller sample sizes. So the Bayesian can win here. And the Bayesian also gets the advantage that because everything's just a probability distribution, the problem really comes down to, can I sample from that probability distribution? It's the same problem every single time. If you can sample from the probability distribution, no matter how complex you make the model, you can give any answer to anything. What's the expectation? What's the variances? What's the covariation between things? What's the distribution of some wild transform? You can sample from it. It's pretty easy to answer those questions. So I think that there's some practical advantages to being a Bayesian, and that's probably what convinced everybody at the end of the day. Probably thought, well, the probability interpretation is nice, but it's all the computational tools that are probably getting people all excited. We used to argue in the 60s, and now you see less arguing. Why? Variational Bayes, MCMC, particle filtering, stuff like that. Is that enough for now? Cool. Good job, guys. I think it was productive.